everybody. I understand from the subject of this particular presentation that there's an interest, of course, in researching and looking at what you need to look at when you're trying to consider the purchase or use of a telemetry receiver. There's all different colors and varieties of telemetry receivers, so I thought maybe we could just go through some of the basics so that you basically have a little bit of a go-by in terms of how to go about selecting a telemetry receiver that meets your requirements. So moving on into what the requirements are, all the telemetry receiver requirements are governed by IRIG 106-19, and the test methods for a receiver are covered in IRIG 118. So those are the two governing documents, of course, that you need to probably refer to or have handy in your library to refer to in terms of some of the requirements of a telemetry receiver in terms of its design and performance. Now, typically a telemetry receiver will either be a single channel receiver, a dual channel receiver, or in some cases a quad channel receiver. And it can be in either one frequency band or it can be in P band, which is 200 to 500 megahertz. The CIF band, the down-converted C band, which is 300 to 1150 megahertz. L band, which is typically from around 1415 to about 1850 megahertz. And then S band, which covers 2185 to 2485. Or lower C band, which is 4400 to 5250 megahertz. These receivers may either be with or without antenna tracking features. And the reason why I mention that is because traditionally receivers are either a data receiver or a tracking receiver. Some receivers can provide both capabilities simultaneously without having an impact on the other. So you can run data at your highest AGC time constants, for example, and while your tracking algorithm is at a fixed time constant that meets the antenna slew rate, so that you can use a receiver for both data and tracking. Still on the ranges, a lot of the ranges still will require and like to have separate data receivers, separate tracking receivers. That's the only reason why I mentioned it. There'll be some receivers that are data only, some receivers that are tracking only, and then other receivers that have both the data and tracking function. A typical receiver is either going to have a single or multi-mode demodulator, which is going to provide one or some or all of those following standard demod formats that I have listed. Traditionally, you have analog FM and PCM FM, NTSC. For international considerations, you'll have a PAL video. You'll have analog and digital PM, BPSK, QPSK, AU QPSK, offset staggered QPSK, trellis FM, which is your tier 0, Artem's trellis FM, tier 1 SO QPSK, and tier 2 CPM. And again, a receiver, depending on your requirements, may or may not need to have all of these demodulator features. Also, it may come with or without a pre-D optimal ratio diversity combiner. We'll talk a little bit more about those. There's also a requirement now with wideband digital recorders that are available on the ranges to where you can now record your pre-D 70 megahertz. And so many receivers in the industry will have a 70 megahertz playback channel where you can play your recorded 70 megahertz back through your receiver. Now, for some of the older legacy requirements, or for those folks that don't want to fully record all of the 70 megahertz IF because of the amount of memory and space that it takes, they'll go with a down-converted pre-D and recording playback feature, which would allow you to basically down-convert the 70 megahertz to a frequency band that meets your requirements and also the requirements of whatever recording device that you're using. So they will be able to have the ability to down-convert to 70 megahertz, record it, and then play it back through the receiver through an up conversion function. A lot of receivers in the industry now contain embedded bit sinks, frame sinks, bit error rate testers, and also PN generators. which is something you want to look at. And if that meets your requirements, it's something that you want to basically make sure you specify those requirements. There are also receivers in the industry that have built-in self-tests, which includes an embedded RF source. So this has a particular application to mobile requirements where you don't have the luxury of a lot of instrumentation in your ground station. And with built-in test and an embedded RF source, you can do a lot of pre-mission setup and pre-mission testing using this built-in self-test feature. Most all industry receivers will also provide the ability to display your eye pattern, your constellation, and also your spectral sweeps. And they will vary in capabilities depending on the particular receiver in terms of what features are available. For example, in spectral sweep, whether you can you have span control, whether you can do center frequency measurements, or whether you can do power measurements when you're observing the spectrum on the receiver display. And then last or not least, the receivers may come with or without TM over IP, which is telemetry, packetized telemetry being transported over Ethernet. So I just threw up a few. These are all SEMCO receivers, a few of the products that we offer, just to give you an idea of what the typical types of front panel interfaces are. The top one is a traditional LCD display with a keypad and menu pad, where you can basically display the different and control the receiver, and also provide different types of displays. The second one is a touchscreen display. This one happens to have two touchscreens to where you can basically run the entire receiver in what I call fat finger friendly touchscreen environment. The one below is one of our tracking receivers, a 1U tracking receiver. That's an Ethernet only, a remote. It's supported by remote control, and that comes actually as either an Ethernet only with a bare front panel, or you can get LCD displays and a keypad if you need front panel displays. But again, I'm just trying to show you that these are the different types of varieties that many of the companies in the industry provide these types of interfaces. The last one that I have down there is a 2U receiver that has a touchscreen, a smaller touchscreen device. And all of the receivers in the industry invariably will have network control via Ethernet. So this gives you an idea of some of the different kinds of rear panels that you'll be confronted when you're looking at a receiver. Typically, you'll have an N connection input for your left-hand and right-hand antenna feeds, BNCs for all your different outputs and inputs, also deconnectors that use cable assemblies. It gives you like an RS-422 and TTL bit sync outputs. You can see over on the left where the power supplies are. You've got a TM over IP panel. You've got a local area network panel. Got a local interface up here with an HDMI display and two USB ports, and then dual redundant power supplies. And the dual redundant power supplies, you'll see two of these products, the one below and the one that I'm just describing. They both have redundant power supplies. This is very popular, and is something that if you're looking for a little bit more security in terms of redundancy for perhaps the issues with power supply failures, that's something you might want to consider is specifying a dual redundant power supply. But this kind of gives you a general idea. Most all industry receivers from whatever company you're buying from will have some type of a panel very similar to this. So the front end of the receiver is probably one of the more important parts of a receiver design. It's usually designed using surface mount and RF component construction. This particular one that I'm talking about provides both L and S band coverage, and it basically interfaces with up-down converter circuitry to support some of the other frequencies other than L band and S band. So in a typical receiver, it's usually a dual super heterodyne design. You'll end up with two local oscillators, the first and second local oscillator. It's very, very important that the local oscillator be tier 2 phase noise compliant, in accordance with 106.19, a very important requirement when you're looking at a receiver. This will basically really is really important in terms of overall receiver performance. In the Agc circuitry, you'll be looking for typically at least 3 different types of Agc outputs or Agc functions. One, of course, is the normal Agc circuitry, which provides Agc outputs that are used for antenna tracking as well as data logging and recording. You'll have Agc 0, which is a function that allows you to zero the receiver either at the noise floor with no signal in, which is a typical pre-mission setup, or to zero it at a pre-designated signal level. And then, of course, Agc freeze, that function is very, very important for using the receiver for antenna G over T measurements. That way you can freeze the gain of the receiver, so you take the receiver gain out of the equation so that whatever gain you're seeing when you're going from, say, hot sky and cold sky with an antenna for G over T, that gain will be the actual gain of the G over T measurement of the antenna. So Agc freeze is an important function you want to make sure is included in your receiver. For AFC, you normally want to have the ability to select AFC loop speeds. Pretty much every receiver out there will have that. That's important to have AFC circuitry that will provide you that loop stress and selectable AFC loop speeds. And also, as part of AFC, to have some sort of a frequency offset, so that if you've got a transmitter that you're trying to track on a test vehicle that is basically is either over deviated or has some sort of a frequency offset, you can basically compensate for that offset in the AFC circuitry so that you don't jeopardize or compromise the mission. You also want to be able to have 70 megahertz. 70 megahertz is the conventional IF for a receiver, for all receivers. And so the first and second LO basically down converts to 70 megahertz and as goes through some very, very extensive RF filtering before that happens. And we'll talk a little bit about that in a later slide. But you want your down converted linear and nonlinear 70 megahertz outputs to be used for filtering and subsequent demodulation by the receiver. Input and processing by the diversity combiner. Pretty much all diversity combiners in the industry use the down converted 70 megahertz from channel 1 and channel 2 to perform the optimal ratio AGC AM diversity combining to provide you the improvement that a combiner can provide. Also routing to other internal devices. And then also a rear panel BNC output for, again, as I mentioned before, your antenna G over T measurements. Now, when I talk about down-converted linear and nonlinear 70 megahertz, the linear 70 megahertz basically is a fixed 70 megahertz, usually at some level, minus 10 dBm, for example, that regardless of signal strength, regardless of the input signal to the receiver, that 70 megahertz will always be around minus 10 dBm. That's very, very important for you to have that capability to have a linear 70 megahertz output as the signal level is fluctuating across the range of the receiver. And then the nonlinear 70 megahertz, of course, is a 70 megahertz that is changing proportionate to the signal strength coming into the receiver. Then, like I mentioned before, the receiver may or may not provide for a switched input for a tape playback from a recorded mission signal. If that's something that you really need in a receiver, that's something you want to specify, is that you want to have the ability to play a recorded mission back through the receiver so that you can basically make some adjustments to perhaps improve on data quality or support issues where you've had some data dropouts. And in a front-end RF tuner, depending on the design and architecture of the particular receiver, it may or may not provide IF filtering circuitry. That filtering circuitry may be provided in another part of the receiver, but typically you'll want to see it up in this front-end RF tuner so that once you down convert to 70 megahertz, you run it through IF filtering circuitry before you pass it on to your demodulator. And typically that uses the SAW filters, the acoustical wave filters, surface acoustical wave filters that provides very, very good shaping and filtering for your analog signals that are coming in. So let's talk about what's critical about your RF tuner down converter parameters. And this is kind of a busy slide, but this is really the heart of a telemetry receiver. A lot of people will say that the heart of a telemetry receiver is the FPGA, the digital FPGA that does all the demodulation, and certainly that's a very, very important and critical part of a receiver. But if you're not presenting a good signal to that demodulator, it's the old garbage in, garbage out scenario. You want to make sure that the receiver is designed such that it basically provides the cleanest, noise-free, filtered 70 megahertz to your digitizing circuit, so that when you digitize that 70 megahertz and do your sampling, you're not introducing any other factors into the demodulation circuitry and the algorithm. So the demodulator is dealing with a very, very clean, the cleanest possible signal that you can provide. So how do you do that? First of all, it starts with your RF front-end filtering. So RF front-end filtering will provide conditioned RF signals for first LO mixing and spurious response suppression. So let's just say, for example, your first local oscillator frequency for an S-band RF input, let's just say it's 390 megahertz. That just happens to be what in our receivers, that's in terms of frequency management, that's what we use for our first LO. It's 390 megahertz. So what you'll want to do is you'll want to present a filtered S-band signal that you've received by that receiver. You'll want to present that to the mixer that's going to mix with the first LO to basically generate that 390 megahertz signal. And right there is where you're going to run into your problems in terms of spurious response suppression, which needs to be below 60 dB. And also, it's the circuitry that creates the noise figure of a given receiver. And you want the noise figure to be as low as possible. We'll talk about that in just a second, a little bit more about what noise figure, the impact of noise figure on a receiver. And then also, even more important than that, the circuitry design needs to start looking at the maximum adjacent channel interference performance that you can possibly get out of the receiver. Now, what do I mean by adjacent channel interference? Obviously, if you have any kind of interfering signals in your bandpass, that is going to present some serious difficulties for getting good quality data. And there are iRig performance parameters that have to be adhered to basically assure that the adjacent channel interference of a receiver will meet the requirements of emission. And so what is normally done is you want to take a look at, say, for example, an interfering signal that's at least 30 dBm higher than what we call the victim signal or the downlink that we are trying to process. And now you have this interfering signal that's 30 dBm higher than that signal. And so the way a receiver is tested to determine ACI performance is you move that interfering signal in close to the bandpass to see when you see degradation, bit error rate degradation in your receiver. And you want to make sure that at the data rate, you set the interfering signal at twice the data rate that you're trying to recover in your receiver, and you move that huge plus 30 dBm interfering signal into the bandpass, and then you determine how close you can get and what the rejection is, where you now all of a sudden see a 1 dB BER degradation. And that has to be at least somewhere out around 35 dBm that rejection has to be for it to be any kind of reasonable ACI whatsoever. And higher the better. 45 is even better. 50 is like optimal. So you want to basically get interested in and take a look at what the ACI characteristics are of the particular receiver that you might be interested in. Now, with your system design, you'll have your first and second LO circuits. They'll be tier 2 noise compliant. You'll have spurious signal suppression, low noise figure, and optimum ACI. Now, what's important in there is the type of filtering that's used for that first LO and for your second LO. The first LO being 390 megahertz. The filtering, for example, I said 390. It could be another frequency depending on what the first LO is. That will change from receiver to receiver. But the second LO will always be 70 megahertz. So, for example, in the case of the 390 megahertz being your first LO, your second LO would then mix with a 320 megahertz LO, local oscillator, phase noise compliant local oscillator, and that would generate your 70 megahertz signal. And now that 70 megahertz signal needs to further be filtered, and we'll talk about that here in another slide. So again, within the front end of the receiver, you also will want to generate your Agc circuitry, which is used for antenna tracking. You want to have selectable fast and slow Agc time constants for signal strength correlation and also antenna tracking. You want maximum dynamic range, precise linearity, and scaling features. Now, what do I mean by that? A dynamic range of a receiver should typically be minus 10 dBm to the noise floor. If it's less than that, it's not going to be a receiver that you're going to be comfortable with. It really needs to be from minus 10 dBm to the noise floor. And the Agc that goes along with that dynamic range needs to be very, very precise, like within plus or minus 0.2 of a dB from minus 10 dBm input down to the noise floor. And at the noise floor will typically be at a 300 kilohertz filter, will probably be about 115 to 120 dBm. That's what you'll want to see in a receiver, is something that goes from minus 10 dBm to around 115 to 120 dBm with a very, very linear, precise Agc output. You also want scaling features on the Agc, scaling features for your antenna tracking, because different antenna control units require either 10 dB per volt or 20 dB per volt. Some of them are even 50 dB per volt. And then if you're doing Agc data logging and you're recording your Agc for post-mission analysis, you want to be able to have a very precise Agc that you can record that would probably be on a different scaling feature than what you would need for your antenna. So that way you could basically have your antenna at 20 dB per volt, for example, and you could be doing Agc data logging at the more precise 50 dB per volt, which is another feature that's very important. I mentioned a little bit before the Agc circuitry, loop stress and selectable loop speeds, and you want to make sure that in the receiver's design that that Agc circuitry is coherent with the same reference signal that's used for the first and second local oscillator. Most all receivers in the industry will have an internal reference oscillator, usually an oven-controlled, very, very precise oscillator. Some are at 5 megahertz, some are at 10 megahertz. But you want to have your Agc circuitry coherent with that reference, which then gives you the best Agc performance that you can expect. Again, the front end may or may not incorporate AM circuitry for antenna tracking. Some receivers use the demodulator for their AM demodulation. That is not always optimum for an antenna. Antennas really like analog AM. You don't have to deal with reconstructed signals. You don't have to deal with latency issues associated with digital processing. So you might want to consider a receiver that has a dedicated analog AM detector that provides an analog output to the antenna and is strictly for antenna tracking. It then gives you the optimum frequency response and low pass filtering that you need for accurate antenna error correction signal processing. So again, the RF tuner front end may or may not provide IF filtering and signal gain circuitry, but at some point in the receiver's circuitry, they have to provide this IF filtering and signal gain. That's the best place to do it, is in the tuner, but some have separate modules or separate circuits that they route the 70 megahertz to for that filtering. So what does this filtering do? It filters for 99% bandpass energy, but that's the goal, is to basically filter out all the noise other than at least 99% of what you want to track and what you want to demodulate. So you basically want to get all the unwanted IF signal rejection out, and IF signal rejection really involves a lot of harmonics associated with the down conversion process. So you always want to be, your goal needs to be to try and make sure that you do not introduce any more noise or any more interfering signals riding along your 70 megahertz when you present it to your demodulator. Now, in accordance with IRIG, 40 dB of IF rejection is pretty typical. There are some superior design approaches that are used, which goes with a serial SAW filter design. So you basically put two SAW filters in series with each other, and you can literally double your IF rejection. You can get up to 80 dB IF rejection. And now that's where you're really providing the cleanest 70 megahertz signal that you possibly can to your demodulator. Again, the front end may or may not provide for that playback of the recorded 70 megahertz 3D signal. Now, if you do have a 70 megahertz playback capability and you want that in your receiver, one of the things that's very important is you have to make sure that the FPGA design in your demodulator of your receiver can support, has an AGC circuit that can support a dynamic input range, because the input range of that 70 megahertz recorded signal is not always controllable. It's always at some level. It's whatever level the tape recorder puts out. And so you want to make sure that you have enough range in the front end of your demodulator to be able to support different input levels of that recorded signal. And typically, you want to kind of look at somewhere in the neighborhood of 0 to minus 60 dBm for an input signal that could be played back through your demodulator. And then again, as I mentioned before, the linear 70 megahertz outputs, when you go into to AGC freeze, you freeze the gain of the receiver, and now that linear output, which is a very precise 70 megahertz, will now move according to the gain of the antenna G over T, and you can make very precise G over T measurements. Some receivers have the ability internal to the receiver to be able to actually make those G over T measurements on the receiver. Some of the receivers in the industry do not have that capability, and you need to have a power meter that you basically put onto that you attach to the 70 megahertz output, and then you measure that the G over T of your antenna using a power meter. So that's again something that you want to consider when you're looking at a receiver. So when you get out of the L and S band world and you need to go into, for example, C band or CIF band, there's all different approaches to doing that. The cleanest approach is to use a C band block up down converter in the front end of this RF tuner. And why do I say that? Because you've gone to all this trouble in the design to make this RF tuner the best tuner that you can design in terms of ACI performance, noise figure, spurious suppression, signal suppression, etc. So you don't want to have to introduce another C-band RF tuner where you have to go with the LO down conversion process and the filtering process that, again, you have to try and run all that now again at C-band and develop another RF tuner. Plus, it's a very costly approach to do that. So the best approach is typically to just use a block up down converter. A block up down converter is a very straightforward, simple design. It takes advantage of the fact that the down converted or up converted signal is coming out of the block down converter now gets processed by that RF tuner, filtered by that RF tuner, and goes through the first and LO designs that have already been optimized for ACI and noise suppression and noise figure. And so you take advantage of the fact that you've already got that design incorporated into the receiver, and then you just use a simple block up down converter to support the additional frequencies other than L and S band. So you can do the 4400 to 5250. You can also do the 200 to 500, and you can do the 300 to 1150 in that manner. One of the things that you also have to make sure that the receiver does when they do take a C-band signal and they go through a down converter, the way iRig has this specified is it basically inverts the spectrum because it uses high side mixer, a 5550 megahertz mixer, requires that for supporting C-band. So you have to have the circuitry in your receiver that basically reinverts that spectrum to get it back to normal. You just want something that you want to just have in your notes to make sure that they have that capability and that they are inverting that spectrum to produce the down converted C-band, 300 to 1150 megahertz. Okay, so that gets us to the digital demodulator, which is basically the FPGA-based part of the receiver. Now, one of the things that really enhances, again, presenting the best 70 megahertz you possibly can to this FPGA for data quality is to now use finite impulse response filters, some FIR filters. So you've already filtered the 70 megahertz with SAW filters, and you've basically got maximum IF rejection with the SAW filter. Now you're presenting that 70 megahertz to the demodulator, to the FPGA demodulator. So now that demodulator, you can develop a FIR filter or a set of FIR filters that can be calculated and presented as a function of the data rate in the demodulation format. So now you can take the filtered 70 megahertz that you're bringing into the demodulator, and you can further filter it to really optimize and really fine tune the 70 megahertz before it gets digitized and sampled. Normally what that does is gives you the ability to present a range of filters that you can either put into an auto select feature. The auto select feature then basically selecting per iRig the IF filtering, the IF FIR filtering that is calculated per demodulation format. To give you an example, PCM FM is typically 1.2 to 1.5 times the data rate. So if you have a 10 megahertz PCM FM signal, you're going to want about 12 megahertz minimum, 15 megahertz maximum of IF filtering on that 70 megahertz. In SOQPSK, it's 0.7 times the data rate because of its spectrum efficiency. So in SOQPSK, for a 10 megahertz SOQPSK signal, you're going to want around 7 megahertz IF. And so you want to be able to have the flexibility to go in there and optimize that IF filtering, both with the SAW filters and with the FIR filters. And one way to do it is in an auto mode, where you have the software do the algorithms and select the filtering that is automatically calculated per iRig format. That way you don't have to sit and try and figure out and try and remember that SOQPSK needs 7 megs at a 10 megahertz data rate. The PCFFM needs 1.2 minimum and 1.5 maximum. You don't have to worry about that anymore because the receiver can actually do that calculation for you. So that's something you want to consider in terms of a feature that is very, very good for you to use, very efficient. So the demodulator incorporates FPGA digital signal processing for all of Artem's waveforms and also the legacy waveforms. These requirements will vary from range to range, and so for your requirements that you're looking at, you can specify which demodulator formats you want in your receiver. So these are the legacy ones include Obviously, PCM, FM, PM, BPSK, QPSK, AUQPSK, those are the basic ones. There's also OQPSK and SQPSK. And then you have the Arden's waveforms, which are the newer waveforms, trellis FM, multi-symboled FM, SOQPSK, and CPM. And these are some of the later demodulator formats that have come online over the last 7 or 8 years. There's also a lot of Fourier correction decoders that has to be addressed. And that really, again, will depend on what your mission requirements are. You may require Viterbi, you may require Turbo, you may require Reed-Solomon FEC. Recently, over the last few years, low density parity check has become a requirement as an FEC decoder. And also, let's see, Viterbi and LDPC, yeah, is an FEC decoder. So then also the FPGA needs to be able to support baseband filtering, again, using FIR filters, and again, can be selected, calculated and selected per data rate and in the modulator format. You also want to make sure that it meets your requirements, and if it's specified by your range capability, to make sure you have NTSC and PAL video capability. You obviously want to have both TTL, digital data, and clock outputs, as well as analog outputs. You need those in both TTL and RS-422. They're both used and required and standard in most all of the range applications. You'll want to look at the requirement for an embedded bit synchronizer. Then you'll need the bit synchronizer to provide digital data, clock, and data outputs. So you'll require an embedded bit synchronizer, which again, a lot of the receivers in the industry provide that. And then some do or do not have a de-randomizer relative to that. And then you also have receivers that also provide you a frame synchronizer, a bit error rate tester, and a PN pattern generator, so that you can do loop testing without any external instrumentation, which is a nice feature to have, but that might be a nice to have feature. Depends on your range requirements. You want selectable AC or DC baseband video coupling. You'll want to look for display capability that includes your eye pattern, constellation, spectral sweep, and EBNO displays and readouts. You want your receiver to have adaptive equalization. Sometimes that's referred to as blind equalization, but adaptive equalization is basically a capability to mitigate RF multipath. And believe me, pretty much every place, every range deals with multipath on a daily basis. And adaptive equalization is a very nice feature, and in many cases a very required feature to support a good data quality. And if you have a requirement to interface with the best source selector, you'll want capability to provide a DQM output, which uses data quality encapsulation to give you a bit error probability capability, and that's provided by the FPGA. And that bit error probability, that information, that data, which is overhead on the actual baseband signal, is used by the best source selectors to make the decision as to which is the best data quality. Last but not least, space-time coding came into being here within the last few years. Space-time coding is a capability that tries to answer the mail in terms of the dual antenna, upper-lower antenna problems associated with a rotating test vehicle, to where you will sometimes shadow one antenna over another antenna. Normally, in a two antenna configuration, you're going to have, let's say if you have a 20-watt transmitter on your test bed, test vehicle, you're going to have perhaps 15 watts coming out of the lower antenna and maybe 5 watts out of the upper antenna. So depending on the rotation and frequency of rotation, you can shadow those antennas and you can get data dropouts. You can encounter data dropouts. STC mitigates that data dropout capability or requirement, and is becoming more popular as time goes on. Not being implemented telemetry wide, range wide. There's a lot of people that probably will never use STC, but in some cases, particularly if you're testing helicopters and aircraft, low-flying aircraft, STC looks like it. It's a real advantage and that you might want to have in your receiver. So then if you basically want to do a diversity combiner, that's where you're going to have a channel 1 and channel 2 input from a dual feed antenna, tracking antenna, and you want to provide up to 3 dBm improvement at equal channel 1 and channel 2 signal levels, then you'll basically want to specify an optimal ratio combining diversity combiner. And it also gives you some other capabilities. For example, multi-path dynamic polarization fading. It's a very significant improvement to a receiver's operation, particularly if you're talking about a dual tracking antenna feed, and you want to try and get improvement in your signal to noise ratio. Combiners also will typically provide you switched outputs where you either have a combined output or you can route your channel 1 demodulated output through the combiner or your channel 2 demodulated output through the combiner. The other feature that you want to take a look at closely when you're looking at a receiver is whether or not the receiver has the ability to zero the combiner function out to compensate for unequal channel 1, channel 2 signal levels at either noise floor or low carrier to noise signals. And what do I mean by that? So in most ranges, you have cabling issues, you have temperature issues on a daily basis, changing from day to day, where channel 1 and channel 2 are going to be moving and fluctuating back and forth. Maybe there might be a 1 dB difference between channel 1 and channel 2. Maybe I've seen sometimes cases where there's 3 or 4 dB difference between channel 1 and 2 because of a bad cable, because of different ambient temperature issues. There's a lot of different factors that go into why the signals from channel 1 and channel 2 with no signal applied, the noise floor is unbalanced. So a combiner can fix that. A combiner can go in and compensate for that by basically zeroing out channel 1 and channel 2 at the noise floor and optimizing that. And this zeroing function can be done right up to T minus 30 seconds, T minus a minute, however, whatever the criteria is for locking down the configuration and setup of your receivers prior to emission. But that optimizes the combiner's performance to try and get the maximum improvement you can out of a combiner. The other thing that's really important is the fade rate of a combiner, the ability to handle a rapid change in signal levels between channel 1 and channel 2, what's referred to as fades, where the channel 1, channel 2 signals are fading back and forth by significant levels during emission. And the one thing that you don't want, of course, is you don't want the combiner to unlock. You want it to stay locked and continue to provide a decent data output signal at very, very high fade rates. And typically what you want is you want something that's equal to or greater to a 50 kilohertz fade rate, to where it can support a fast fades that are occurring between channel 1 and channel 2. Also, the combiner needs to have a best source select switching capability, to where you can convert the combiner into a best source selector for selecting the highest carrier to noise signal between channel 1 and channel 2, so that you aren't basically losing your data because the fade is so deep that the combiner stops combining and you basically lose the signal. So what you want to do is you want an automated best source selection, and you also want manual best source selection. So you could go in and you can basically put the combiner into a manual best source select mode. So now we'll talk a little bit about features that, again, I mentioned to you before, that are becoming more and more prevalent in receivers in the industry. Not all of them may have it, or you may not have a requirement for it. But that's embedded bit sync, frame sync, and bit error rate testers that are part of the receiver design. So, you'll be looking for at least a dual channel bit sync, frame sync, and Bert. You'll need a rear panel BNC to DB connector cable harness so you can get your RS-422 and TTL outputs. You want the bit syncs and frame syncs to handle up to 40 megs in NRZ. You want to have Viterbi and turbo code FEC decoders. You want switchable input impedance so that you can go either high or low for your input impedance. Again, TTL and 422 outputs. You want at least a 32-bit frame sync and word length, programmable up to 65,000 words. And then you want a PN generator that provides all the standard PN patterns for your BER testing, which then is provided by the Bert. This is a very, very important feature to have in a receiver, particularly, as I mentioned before, where you're in an environment where you have limited access to instrumentation in your racks, where you can do this with external instrumentation. And I mentioned to you before about pre-D record and playback. Typically, the pre-D record and playback features that you want to look for is at least to be able to support 75 kilohertz to 15 megahertz in 1 kilohertz steps for your down conversion and your playback up conversion. So what does that mean? Well, that means that 15 megahertz down conversion, if you multiply that by 1.4, you know, you're talking about being able to support a 22 megahertz data rate. So with this pre-D down converter, you don't have to record the entire 70 megahertz. You can basically record something that's a lot closer to the actual data rate that you're tracking. And so this pre-D record and playback capability allows you that capability. So then you have user adjustable gain levels, and then you have your channel 1 and channel 2 tape playback to where you can literally play the mission back again through your receiver, which is a very, very, very good feature to have. Now, normally what happens when you have this capability is what you do is you bypass all the front-end RF filtering of the receiver, and you inject the playback signal. In this particular case would be like, for example, I mentioned to you the 390 megahertz first LO. You would be injecting an up-converted recorded signal at 390 megahertz into the receiver and then playing that mission back completely through the receiver as if you were running the mission for the first time. So last but not least is TM over IP, telemetry over Ethernet. Important parameters for successful TM over IP data transport from TM receivers includes the ability to do PCM, TM over IP, and that needs to support both IRIG 218-10 and then IRIG 106 chapters 4 and 8 format 1 data. And that's the data that you really need to be able to packetize and transport over Ethernet. You also need to have the capability of supporting chapter 10. Chapter 10 is used in many cases a lot more than IRIG 218 because it is a more standard format and also because tape recorders also do chapter 10. And so it's a standard format that's used in TM over IP. You have to be able to support the DQM interfaces for use with best source selectors. You also need to be able to support dedicated output connection that auto detects at 10, 100, or 1,000 megs, operates over UDP or TCP connections. What happens is the receiver's demodulator routes recovered clock and data signals to an embedded TM over IP design, which then transports packetized data packets via Ethernet to designated reception device. And one of the most important things that you need to be able to do is you need to be able to time these packets. You need to be able to do IRIG or network timing. And so the receiver must have the capability to insert an IRIG time tag if you're not going to use network timing. So I've gone through a lot, and I've gone through it relatively quickly, I hope. But in summary, telemetry receiver requirements and features described in this presentation. As I mentioned before, they're not necessarily in every industry receiver, and your final receiver requirements must be tailored to your unique requirements. However, critical receiver parameters that are applicable to every telemetry receiver that you're looking for includes examination of the front-end RF filtering and signal conditioning for optimum noise figure, adjacent channel interference, and spurious response. Let me speak one moment too. I kind of forgot about this. I passed over noise figure a little bit. Keep in mind that when you go to IRIG 106, IRIG 106 will say that the noise figure of a TM ground station needs to be less than 12 dB to ensure that you don't degrade the bit error rate performance and data quality to where it's unusable data. So does that mean that everything needs to be to 12 dB? No, that doesn't mean that. What it means is if you take the cascaded noise figure formula, it takes into account the noise figure of the low noise amplifier, the antenna's low noise amplifier, which is typically around 1 dB, 1.5 dB. You take in the noise figure of, say, a typical multi-coupler that's basically routing and distributing the RF to multiple receivers. Then you take the noise figure of the receiver and you put it in this cascaded noise figure equation. And what you find out is that the receiver doesn't degrade the noise figure of the front end. In other words, it doesn't override or suppress the noise figure of the low noise amplifier or the multi-coupler until it reaches around 10 dB. Around 10 to 11 dB, you'll start seeing a little bit of degradation in the front end. What kind of degradation am I talking about? I'm talking about somewhere about 1/4 of a dB. So when you're looking for a receiver out there, you want to take a look and make sure that the noise figure of the receiver is somewhere between, say, 8 to 10 dB. And that will be just fine. You won't have any problems with that receiver if it's down in that area. Don't get really excited about, say, for example, a receiver that says, well, look, my noise figure is like 4 dB or 5 dB, and so I've got really good noise figures, so you're going to get really good data quality. Turns out that if you crank in the equation and you crank in a noise figure of 4 or 5 dB at the receiver, along with the LNA and the multi-coupler, and you crank in the same equation, you look at, say, 8 dB or 10 dB, you're not going to see, you won't be able to even detect the difference in BER degradation. So 8 to 10 dB is going to be just fine for when you look at a receiver. And I just wanted to leave you with that. You need to make sure that IF filtering and preferably saws and a combination of saws and FIRs are used for capturing the 99% of bandpass energy and optimizing rejection of unwanted IF signals in the bandpass. You want to take a close look at the linearity and the accuracy and the scalability of the AGC outputs. You want to take a look at the fast AGC time constants. You want the fastest AGC time constant for optimum data quality, and you want a slower fixed AGC time constant for antenna tracking. You need to take a look and see if the receiver actually provides you both of those capabilities, or whether or not you have to look at a receiver as strictly a data receiver, and then basically look at a dedicated tracking receiver with a slower AGC time constant. You want to make sure that the receiver provides linear 70 megahertz IF outputs to provide your antenna G over T measurements. In the industry, analog 70 megahertz is preferable. Reconstructed digital 70 megahertz tends to provide some problems in that regards. You want to have the capability for a multi-mode FPGA demodulator with AGC, dynamic range input, and also baseband FIR capability that provides your BER performance per IRIG. And when I talk about a multi-mode FPGA demodulator, you want to make sure that you have a demodulator that, even though you might not need a particular modulation mode now, 3 or 4 or 5 years from now, you may need another mode loaded onto that FPGA. And so you want to make sure you have a big enough FPGA and a expansive enough FPGA to where you can add capability to your receiver as time goes on. You also want to make sure that there's AM outputs that have selectable output impedance, low pass filtering for the optimum processing of antenna error correction signals. Now, other receiver features, as I've talked to you about in this presentation, diversity combiner, 3D record and playback, 70 megahertz playback, adaptive equalization, data quality metrics, FEC decoders, space-time coding, eye constellation and spectral sweeps, bit sync, frame sync, Bert, PN generator, built-in self-test, and TM over IP, all of those are becoming more and more the norm as a function of ongoing range modernization programs and emerging technologies. And so you need to look at that in terms of not necessarily what you might need today, but what you may need in the future as time goes on. So I thank you for your time. We can open it, I guess, Ryan, you can open it up to some questions if you want.
Yeah, absolutely. I appreciate that, Bill. Great job. You covered a lot and very succinct. Couple questions right off the bat from the audience. First one is in regards to your power supplies, the dual redundant power supplies. Are they hot swappable? And follow up, what notification do you get when a power supply goes down?
Well, the answer is yes, they are hot swappable, and you get both an audio and a visual indication. The power on off light on the front panel flashes, begins flashing, and you hear an audible tone that you can reset on the power supply. If you want to continue running the receiver on one power supply, you can reset the audio so it doesn't become an irritation. But the power on off light will continue to flicker until such time as you replace the defective power supply.
Perfect. Thank you so much. Another question from the audience is in regards to your built-in self-test. Question, does the built-in self-test have an output? Is the output power adjustable?
You can route the power output, but it's at a fixed level right now. We basically have it at a fixed level for internal BER testing internal to the receiver. We can put, when we've talked about putting a gain control on that, if you wanted to be able to adjust the output externally, basically provide an output that you could adjust on the receiver. That hasn't come up as a requirement, but that's not something that's hard to do.
Okay, something worth considering there. Another question regarding upgrades. What is possible for getting an upgrade of an old SEMCO receiver?
Well, we have a program ongoing right now where we can literally upgrade any legacy receiver that we produced from the year 2003 up until now, till 2020. We can convert and upgrade those receivers to our 3U Linux platform, the RC300. We offer those upgrade programs at a fairly significant reduction in cost to the cost of a new receiver, and we offer our standard 2-year warranty on the upgrade program. So it gives the customer who's been using legacy SEMCO receivers for some time, years, to be able to upgrade to a non-Windows based Linux RC300 receiver. And we basically reuse some of the modules and cards that come out of the older receivers. Some of the design architecture is the same. And in cases where we can't reuse it, we replace it with the newer hardware. But yeah, we do that. We've been doing that for quite a while for several of the ranges where they're heavily invested in SEMCO receivers, and this is a very cost-effective way to support their range modernization program and also provide them more IA compliant and cyber secure receivers.
Fantastic. And I'll just add that we did include in the handouts for the webinar, we did include a one-page description of the upgrade path on the SEMCO receiver. So there's a little bit more detail on that. And a couple more questions coming in here, Bill. Do you support Chapter 7?
For TM over IP?
What the question's referring to. Are you doing anything with Chapter 7 at this point?
I believe so, but that's a question I would have to defer to engineering on that to find out. I'm not that familiar with it.
Okay. Another question here. Can the Bert test signal be routed out to the system?
Say, for example, using the Bert in one receiver to do a Bert in another receiver?
Yes.
Yes. We have an option that you can put into the receiver for providing an external input to the embedded bit sync. So by providing an external input to the embedded bit sync, you can basically bring an external signal in, an external TTL clock and data signal or analog signal in from another source, and use the embedded Bert to do your BER.
Okay, I think great answer there. Last question, I think, and we're going to wrap it up as we've covered a full hour here. How much support do you offer? What kind of requirements are you seeing out there on those legacy mod formats that you were talking about?
Well, for all the spacelift programs and all the ICBM programs, we're going to see legacy for a long time. And so we routinely provide in our receivers a multi-mode capability that includes both legacy and the later ARTEMS DMOD formats. That comes standard. That's not an option. So that way, even if you only are using, for example, PCM, FM, and SO QPSK, which some of the ranges are standardizing on, you still have the ability to do QPSK, AQPSK, AU QPSK, all the other DMOD formats. They all come as a package. But in more succinct terms, both the Eastern Range, Air Force Eastern Range, and Air Force Western Range, they still extensively use the legacy DMOD formats, as well as some of the other selected ranges.
Sounds good. Sounds like there will be support for some time to come.
Oh, yeah.
Okay, good. Well, I think that about does it for our time slot. I think it was a great topic, great information. We've made the slides available in the handouts here, and they will also be sent out as part of the package that gets sent out after the recording's done. So that'll be sent out tomorrow. And just again, thanks so much for your time and energy. I know it takes time to do this, Bill, and we really appreciate it. Thanks to the customers out there and to the local teams for tuning in to Tech Tuesday from SEMCO. We really appreciate it. Thanks again, Bill.
All right. Thank you.